Earth's cozy atmosphere and gentle blue skies give us a highly biased, incredibly comforting view of physical reality. We look up at night and see a quiet, peaceful tapestry of stars. But that sense of calm is an illusion. Our brains evolved to survive on a predictable, oxygen-rich rock. We are simply not equipped to instinctively understand the extreme physics of a chaotic, frictionless vacuum. So let's put your earthly intuition to the test. We're going to run through a series of 10 cosmic scenarios. For each one, I want you to guess the outcome before I reveal the physical reality. You will quickly see that logic based on Earth's rules fails entirely out in the dark. To actually comprehend the universe, we have to rely on rigorous scientific measurement. Keep track of your score. Let's begin. We start in the pure vacuum of space. Here is your first test. If a massive supernova exploded just 10 miles away from your ship, what would it sound like? The answer is absolute dead silence. Sound waves aren't physical objects. They are mechanical vibrations that require a medium, like compressed air molecules or water, to travel from a source to your eardrum. Because space is an empty vacuum, there is nothing for the explosion to vibrate against. Moving to test number 2. What happens when two perfectly bare pieces of identical metal touch in this vacuum? They fuse together permanently. On Earth, oxygen creates a microscopic oxidized barrier on metal surfaces. In space, that barrier doesn't exist. When those pure metals meet, their atoms share electrons seamlessly, entirely unaware they're supposed to be separate objects, in a process called cold welding. Try test number 3. How long will the footprints left by the Apollo astronauts remain on the lunar surface? The answer? At least 100 million years. Look closely at the distinct boot tracks pressed into the dust next to the astronaut in this photo. Because the moon lacks an atmosphere, there is zero wind to disturb the surface and no water to wash anything away. Unless struck by a rogue meteor, those prints are perfectly preserved. A vacuum is defined entirely by what it lacks. Without active forces like flowing air or liquid water, space creates an environment that halts deterioration, freezing history in place and seamlessly fusing matter. Let's scale up to planetary bodies. Test 4. Can a planet's single day last longer than its entire year? Yes, and it happens right next door. Venus takes 243 Earth days to complete a single, agonizingly slow rotation, but only 225 days to orbit the Sun. Because heavy clouds obscure the planet, astronomers had to bounce radar waves off the surface and measure the returning echoes to map this incredibly sluggish backward spin. Test 5 takes us outside our solar system. What precious material makes up a massive portion of the exoplanet 55 Cancri e? It turns out to be solid crystallized diamond. This chart illustrates transit photometry. When an exoplanet passes in front of its host star, the star's total light output dips slightly. By analyzing that tiny shadow, scientists can calculate the planet's exact size and mass. By running that specific light signature through a spectrometer, astronomers essentially read the planet's chemical barcode. For 55 Cancri e, the data reveals an extreme density of carbon. Under the crushing pressure of a world baking at over 3,000 degrees Fahrenheit, that carbon physically crystallizes into solid diamond. The passage of time and the composition of the rocks beneath your feet are not universal constants. They are wild variables dictated entirely by extreme local conditions. Let's push those conditions to their physical limits. Test 6. When a massive star dies, how fast can its collapsed core spin? The answer is up to 600 times per second. This extreme rotational velocity is driven by the conservation of angular momentum. Just like a figure skater pulling their arms inward to spin faster, when a colossal star violently collapses into a tiny, hyperdense neutron star, its rotation multiplies exponentially. Test 7 challenges your sense of scale. Where is the largest body of water ever discovered? It is floating around a distant quasar, locked in a vapor cloud large enough to hold 14 trillion of Earth's oceans. We obviously can't send a probe to verify it, so astronomers use highly sensitive radio telescopes and spectrometry to detect the exact light signatures emitted by water vapor molecules floating 12 billion light-years away. This visual comparison shows the massive volume of our local star. If the Sun were a perfectly hollow sphere, you could drop 1.3 million Earths inside of it. A human mind cannot intuitively visualize a spinning object that heavy, or a volume of water that massive. We have to rely entirely on mathematics and distant light data to comprehend these objects. Which brings us to the ultimate limit. Test 9. The universe is approximately 13.8 billion years old. So how wide is the observable universe? A measured width is 93 billion light-years across. That creates an apparent physical contradiction. If nothing can travel faster than the speed of light, how could the outermost edges of the cosmos travel 93 billion light-years in only 13.8 billion years? This grid animation demonstrates the solution: metric expansion. The galaxies themselves are not physically flying through space at impossible speeds. Instead, the actual fabric of space sitting between them is stretching, continually creating new physical distance. We measure this through a phenomenon called redshift. As a beam of light travels toward us from a distant galaxy, the expanding fabric of space physically elongates the wave itself, stretching it into the red end of the light spectrum. The strict absolute speed limit of the universe only applies to objects moving within the vacuum. It does not limit the expansion of the vacuum itself. Let's bring this back to your own body for the final test. Where did the specific atoms of iron pumping through your blood and the calcium forming your bones originally come from? They were forged in the hearts of dying stars. Through a physical process called stellar nucleosynthesis, the extreme heat and pressure of massive supernova explosions force lighter elements to fuse together, creating the heavier elements required for biology. That violent physics is literally responsible for constructing you. As Carl Sagan noted, we are made of star stuff. Our earthbound brains may struggle to predict the silence of the vacuum or the stretching fabric of a 93 billion light-year void, but the very atoms we use to measure those anomalies prove we are an inseparable part of that exact same chaotic system. So, how did your intuition hold up against physical reality? Let me know your final quiz score out of 10 in the comments below. And if you want to keep exploring the mechanics of the universe, hit that subscribe button. Keep looking up, and I'll see you in the next one.